Okay, so today I'm going to go through this presentation with you about photoelectron spectroscopy. This is a kind of a big word that basically is saying a way that we can understand atomic structure, a way that we can understand electron configurations, as well as ionization energy and periodic trends. So what we're going to do is we're going to, first of all, kind of talk about what photoelectron spectroscopy is, and then we will go ahead and kind of talk about how to read the graphs that are produced, the data that comes from the photoelectron spectroscopy. So what is PES? PES is photoelectron spectroscopy, kind of the abbreviation. So it is a way to use photoelectron spectrophotometers to use the high radiation, high energy radiation, X-rays or UV rays to eject electrons from an atom. It usually inputs only one type of radiation with a specific energy. So we want to know how much energy comes from the spectrophotometer, so we just use that specific energy. And because electrons within an atom are in different energy levels, different electrons require different amounts of energy to eject. If you think about Coulomb's law, what we've been learning about the last couple days, if an electron is closer to the nucleus, it's going to have a greater force of attraction to the nucleus, and therefore be harder or require more energy to remove. So electrons that are closer to the nucleus are harder to remove. Valence electrons are easiest to remove. And for the most part, what we deal with in chemistry and what we like to focus on are those valence electrons. What PES allows us to do is to focus on the electrons that are those core electrons, those ones that are closer to the nucleus. It also removes electrons from multiple atoms, so electrons from all levels will be observed and graphed. So all those S, P's, D's, F's electrons, those will all be removed from the atom. So what is measured? So we send a beam of energy into or at an atom, and any leftover energy determines how fast the electrons are moving when it leaves the atom. So we will take the energy, shoot it at an atom, and that will allow the electron to be removed, causing there to be positive ions formed. And whatever speed that electron is traveling at will tell us how much energy it was used to actually remove it from the actual atom. So if only a small amount of energy is needed to remove an electron, a lot of energy is left over, these electrons will be moving really fast. So if this electron is traveling really fast, that means that all of this energy, or a lot of the energy, is still in the electron, and therefore it did not require a bunch of energy to remove the electron. If a large amount of energy is needed to remove an electron, that means that not much energy is left over, and these electrons, because so much energy was used to remove the electron, the speed of the electron will be very slow. So from this we can get graphs, and this is kind of the big part of the way we use it in AP chemistry, is reading these graphs. So you'll be given a graph that looks something like this. The y-axis will be something having to do with electrons. So number of electrons, relative number of electrons, or the signal intensity. The x-axis will be something to do with energy, ionization energy, binding energy, or it'll have this little symbol. And the units here will be megajoules per mole, or electron volts. One other thing of note is that the x-axis is numbered backwards. So most of the time when you see a graph, The 0 will be here, and it'll be going up as you go right. In this case, the highest numbers will be on the left, and the numbers will proceedingly go down, decrease. Also, it will also be in, a lot of times it'll be in a log scale. So notice this isn't going by ones or tens or hundreds. It's going by powers of 10. So 1,000 to 100 to a 10. And again, that's simply for ease of use in reading, because the scales can be quite large. You might also see a break where there's like 2 little dashes or 2 little lines where it'll break and just totally disregard some units. So here's another example of how to read them. The height, again, tells you the number of electrons at that particular specific energy level. So you'll see these peaks, and the height represents a number of electrons. So if there's more electrons, it's going to be taller. If there's less electrons, it's going to be smaller. The ones closest to the peaks that will be closest to the y-axis require lots of energy to remove the electrons. Those are going to be your inner shell. The ones closest to the nucleus, the hardest to remove. The ones that are further to the right, those are going to require the least amount of energy. Those are furthest out, most likely your valence electrons, and they'll be easiest to remove. Location tells how much energy is required to move the electron. So here's a few samples of what you might see. This kind right here will be, let me go up a little bit. This kind right here will be pretty common. These are not as common. You won't see those as much unless you're working with an actual spectrophotometer. But this is kind of what you're going to see. So let's go through a couple examples. So here is hydrogen's photoelectron spectrometry graph. Hydrogen is unique because it only has 1 electron. So if you look on the y-axis over here, we have number of electrons. On the x-axis, we have energy. So what this means, and the 1.31 is the actual amount of energy required to remove that electron. So that is the 1 peak for its 1 electron. Okay. So if we scroll down to helium, notice it has only 1 peak because it has 2 electrons. It's taller. If I go back up to hydrogen, it was out here, and then helium is here. So it's a taller peak because it has 2 electrons, but still only 1 peak because those 2 electrons are in the same orbital, the 1s orbital. Also notice that the energy required went up. Why is that? Because helium has 2 protons in the nucleus versus hydrogen only having 1. So it has a greater effective nuclear charge and therefore harder to remove the electrons from. Then we get to lithium. Here's lithium. Notice we added another peak. Why did we add another peak? Well, these are your 1s electrons. Then this would be, because we're starting a new energy level, these would be your 2s this would be your 2s electron that lithium has. So it's further out, therefore it's going to require less energy to remove. These, again, if I look, these are the same electrons that a helium has, but now it's 6.26 megajoules per mole instead of 2.3. Again, because we're adding that extra proton to the nucleus. So here's beryllium. Now it has 1s2, 2s2. So we have these 1s electrons and then the 2s electrons. And notice there's 2 electrons. If you look, the height has the 2 electrons in both the 1s and the 2s. And if we move to boron, now we have another peak that shows up because the 1s and the 2s are full. So now we get to P, the 2p for boron. So So this is kind of another way of representing that we can represent electron configuration. So here we have this little peak, that's your 2p, 1s, 2s, 2p. Okay, and there's only one electron because, again, boron just has those 5 electrons. So if you can count up all the peaks, 2 for each of these and one of those, 5 total electrons, that's how many boron has. That's boron's atomic number. If we move on, here's carbon, 1s, 2s, 2p, 1s, 2s, 2p, and this, they all have 2 electrons in them. Now we have nitrogen, and look at this peak here. Why is this peak taller than these two? Well, this peak has 3 electrons because this is the 2p orbital. The 2p orbital has 3 electrons in it for nitrogen. Okay? And again, if you keep on looking at this peak, the energy keeps going up and up and up because we have more protons coming to the nucleus, and therefore it's going to be harder to remove those electrons. Oxygen, now we're adding another one to this peak. Okay, 2p4, that is. Here's 2p5 for fluorine, 1s2, 2s2, 2p5. All right. And then we have neon. Neon has 6 electrons, and it's a full shell, so it has 2p6. Again, I can't emphasize it enough. This number, these numbers, as we keep going down, or keep adding more protons and electrons, those numbers keep going up because it becomes harder and harder to remove the electron. Now here's sodium. Now we have 1s2, 2s2, 2p6. Then here's a little peak here. What's that one? Hopefully you said 3s1. Okay, so 1s2, 2s2, 2p6, 3s1 for sodium. And now we have magnesium, 1s2, 2s2, 2p6, 3s2. Okay, so a question might say how many different orbitals are present, and again you'd count the peaks here. That's how many orbitals: 1s, 2s, 2p, 3s. Here's aluminum: 1s, 2s, 2p, 3s, 3p for aluminum. One electron in the 3p. Here's silicon. Now it has 2 electrons in the 3p. Hopefully you're seeing some patterns form. Here's phosphorus, 3p3. 1s2, 2s2, 2p6, 3s2, 3p3. And how do I know it's 3? Because look at the number of electrons in that peak. Here's 3p4 for sulfur. Just going to quickly go through, this video is getting long. So 3p5, 3p6 for argon, and there's 4s1 for potassium. Okay, we'll stop the video there. I hope you understand it a little better. Let me know if you have any questions.